In the previous few lectures, we were discussing about some exact solutions of Navier Stokes equation for steady flow. In reality, many flows are unsteady flows, and today we will learn how to obtain the exact solutions for Navier Stokes equations for two special unsteady flow problems, very classical problems. One is Stokes first problem and another is Stokes second problem. So, Stokes first problem. Let us say that you have a plate, there is a fluid which is on this side of the plate, this fluid is standstill as the plate is not moving. Suddenly you drag the plate towards the right or left, whatever, with a velocity u0, and this plate tends to drag this fluid along with it. Our point of interest is that how the velocity in this fluid, assuming Newtonian, Stokesian, whatever, all those traditional considerations that we have made in this course, how the velocity in this fluid varies as a function of position and time. So, when we say position, it is ideally a 3-dimensional problem, but if the width of the plate is infinitely long, then it is still a 2-dimensional problem. So, now if you think of a coordinate system x and y, because the plate is pulled along the x direction, the predominant effect is the velocity variation or velocity along x direction, but the variation is with respect to y, because when can variation of velocity with respect to x occur? It can occur had this u0 been a function of x, but this u0, the pulling velocity is not a function of x. So, because of uniform pulling along x, this problem is having a translational invariance with respect to x. Please train your students not to get confused between this and fully developed flow. So, here u is not a function of x because of translational invariance. That translational invariance comes from the boundary condition, but fully developed flow comes from a very important fundamental premise, that is the flow is confined in a closed passage, a channel, pipe, like that. In an open flow like this, there is no such concept of fully developed flow. So, because u is not a function of x, u is a function of y and t or t and y, whatever. So, the governing equation, let us write the Navier Stokes equation along x. Okay. First of all, if you assume 2-dimensional incompressible flow, Okay. Out of this, this is 0 due to translational invariance, therefore V is not a function of y. Because V is equal to 0 at y equal to 0, no penetration boundary condition. This means that V is equal to 0 for all y. So, here u is not a function of x, so this is 0, V is equal to 0 for all y. Here u is not a function of x, u is of course a function of y. This is a flow which is unbounded and there is infinite fluid, so the pressure gradient which is acting is 0 because everywhere it is atmospheric pressure. So, you are left with this equation, let me write at the top. What is this nu? This is called as kinematic viscosity. Why is this kinematic viscosity important? See, viscosity is the ability to create momentum disturbance, and so if you have a plate, when the plate is moving, by virtue of the fluid property viscosity, this message of movement of the plate is propagated to the outer fluid. But the outer fluid, because of its inertia, tries to retain its earlier momentum, that is the condition of rest in this example. And because mass is a measure of inertia and density is related to mass, so this is essentially representing what? Ability of the fluid to create a disturbance in momentum relative to its ability to sustain its momentum, and that is the physical reason, physical meaning of the kinematic viscosity. So, kinematic viscosity is a very important parameter. It is not just the viscosity, viscosity tries to diffuse momentum, but there is something which tries to sustain momentum, and their relative importance is a matter of concern. So, this is also a very important point when you teach your students about kinematic viscosity. Do not just define it as a property, but try to give a physical meaning to why this is important. So, now I will keep the figure, but erase the remaining part of the board. Here you see that this equation has certain scales involved. What is the scale? For example, the scale of u is the maximum u, maximum u is u0. What is the scale of time? There is no such scale, because you start with time equal to 0, you can go up to time equal to infinity. Time is like your independent variable. So, let us say that we are interested with a time scale of t and see what is happening at that scale. So, this symbol, this tilde is of the order of, so this is of the order of u0 by ts, where ts is the time scale at which we are interested. It can be anything from 0 to infinity. This is of the order of nu, this is the length scale, also unknown. What is this delta? This delta is how much thickness of the fluid responds to the movement of the plate at a time t equal to ts. So, beyond this delta the outer fluid does not understand that there is a plate which is moving, because there the velocity remains 0, only within this delta layer the velocity changes. So, why this is u naught by delta square, this is del y of del u del y. So, 2 times derivative with respect to y, and velocity scale is there only in the numerator. So, you have, so this is of the order of u0 by delta. So, another del y of this makes it u0 by delta square. So, now we can say one thing, that because these two terms are equal, they must be of the same order, because there is no other term to cancel these two terms in the momentum equation. So, if you equate the order of these two, then you can write delta is of the order of square root of nu into Ts. So, at a time Ts, you get a feel of what is the order of magnitude of the penetration layer. Now, this problem, if you allow more and more time, let us try to make a plot of how the velocity is expected to vary over position and time, just qualitatively. So, if you make a plot of the velocity, this is your x axis, this is your y axis. So, the velocity at the boundary is u0, this boundary condition remains. So, this is t equal to t1, then this is t equal to t2. In this way, this is say t equal to t3, where you have increasing t in this direction. So, what is happening is, as you allow more and more time, more and more thickness of the fluid is responding to this movement of the plate. So, the velocity plots are all scattered, this is x axis is u and y axis is y. However, you can collapse all these data in the form of a single variable if you try to understand the similarities of these. What is the similarity? The similarity is that u by u0 is a function of a single variable eta, where eta scales with y by delta. Okay. This is your expectation, and this expectation will be true if you can convert this partial differential equation into an ordinary differential equation. If you cannot convert, if you are not in a position to convert this, it is not possible, then such a similarity does not exist. So, it says that u may be a function of y and t, because this delta is a function of t, but u by u0 is a function of a single variable eta, which itself includes both y and t. So, let us say eta is equal to y into g of t, where g of t is scales with 1 by delta. So, now let us consider this equation. dg dt, okay. Then I am just writing all the terms in the governing equation. So, we can write, because these two terms are equal, now you can also write y as eta by g. So, we can write, you can cancel u naught from both sides. So, you can write okay. So, now see, we have been successful in separating the variables. How we have been successful? This is a function of eta only, and this is a function of g only, sorry, function of t only. So, a function of eta only is a function of t only if each is a constant, okay. So, this implies this one. So, you can write okay. So, let us take this part. So, you can write g to the power minus 3 dg. So, g to the power minus 2 by minus 2 is equal to c nu t plus c1. Now, what is g? G scales with 1 by delta. So, what is delta? Delta is the penetration depth, that at a given time t how much of the fluid understands the effect of movement of the plate. So, at time tends to 0, delta 10 will be 0 because the plate movement has just started. So, then g will tend to infinity. So, at time is equal to 0, g tends to infinity, that means C1 is equal to 0. So, you can write g is 1 by square root of minus 2 c nu t. So, see, out of a rigorous mathematical exercise, the simple thing that g scales with 1 by square root of nu t is recovered, because g scales with 1 by delta and delta scales with square root of nu t. So, this is the power of order of magnitude of scaling analysis, that whatever could be recovered from very involved elaborate mathematics, from pure intuitive physical arguments, the same thing could be recovered. So, now what are the values, possible values of C? C could have a value of anything, but it has to be negative, because G has to be real. So, C must be negative. So, as an example, you choose C is equal to minus 2, okay, which is not a must, not a must, you can choose any other value. Remember that in ratio proportion problem in school level, when you have A by B equal to C by D, you can choose each equal to K, whatever is the K, it does not matter so long as A by B equal to C by D. Same thing here. So, A by B equal to C by D is equal to C, does not matter what is this so long as it is physically realistic. So, if you choose C equal to 2 minus 2, the good thing is that you have this 2 out of the square root and you are having this as the form of GT. So, then you have now let us, so this is a very simple ordinary differential equation to solve. Let us clean up the remaining part of the board so that we can do it quickly. So, let df d eta is equal to h. So, you have dh d eta plus 2 eta h is equal to 0. So, you have dh by h is equal to minus 2 eta d eta. So, ln h is equal to minus eta square plus ln k. Okay. So, h is equal to k into e to the power minus eta square. We will put f and this as 0 to eta plus some k1, right. This is the solution to the problem. You require two constants k and k1. So, we will give two boundary conditions. What are these? The first one is obvious, at eta is equal to 0, that is y is equal to 0, you have u equal to u0, that means u by u0, that is f, which is equal to 1. This is boundary condition number 1. So, you have 1 is equal to k1, right. Then the boundary condition number 2, at eta tends to infinity, you have f equal to 0, because the fluid at infinity does not understand the effect of the solid boundary. So, if it does not understand the effect of the solid boundary, then 0 is equal to okay. So, now integral 0 to infinity e to the power minus eta square d eta, let eta square is equal to z. So, eta is equal to z to the power half. So, d eta is half z to the power half minus 1 dz. So, this becomes 0 to infinity e to the power minus z to the power half minus 1 dz with a half outside. This becomes gamma of half. where gamma is the gamma function, e to the power minus z into z to the power n minus 1 dz, and gamma half is root pi. So, this is root pi by 2. So, k into root pi by 2 plus 1 is equal to 0, that means k is equal to minus 2 by root pi. So, f will be equal to 1 minus 2 by root pi 0 to eta e to the power minus eta square d eta, right. This by definition is error function. So, 1 minus error function of eta, right. This is also known as complementary error function. So, this is the solution to the problem. Now, if you make a graphical plot of f versus eta instead of u versus y, where at different times you have different characteristics, you just make a plot of u by u0, which is f, versus eta is y by 2 square root of nu t, right. So, you will get a graph like this. This is 1 and this is roughly 2, right. So, all the results have collapsed in the form of a single master curve. So, you can understand that you have more time, you have more the penetration depth y, but beyond this eta is equal to 2, the outer fluid does not understand the effect of the movement of the plate. So, this gives a nice physical insight to the problem. Although technically at y tends to infinity, below that any fluid will feel the effect of the plate, but for all practical purposes beyond this non-dimensional thickness, the fluid does not feel the effect of the plate. We will consider the next problem now, which is the Stokes' second problem. So, here the only difference with the previous problem is that instead of a plate moving along a particular direction, it is oscillating with, let us take this as an example. All other considerations of the previous problem remain the same. So, the governing equation remains the same, only the boundary condition at y equal to 0 changes. So, if you do a scaling of this, and this is of the order of, so far so good, but this problem has a unique TS. In the previous problem that you could vary at your will, but here the TS is governed by this 1 by omega. This is the most important physics of this problem, other part is just trivial mathematics. So, if Ts is of the order of 1 by omega, then you have omega u0 is of the order of nu u0 by delta square. This means delta is of the order of square root of nu by omega. It does not vary with time, it is a fixed order of delta which is governed by nu and omega. So, now we can non-dimensionalize this equation. Let us say you have u non-dimensional as u by u0, t non-dimensional as t by ts, where ts is 1 by omega, y non-dimensional is y by delta, where delta is square root of nu by omega. If you put the relevant scales in this equation, you will get because all the coefficients will be absorbed in the non-dimensional parameters. You can easily check that in this equation if you substitute all this. So, there are many ways of solving this equation. I will show you a simple trick to solve this equation. So, assume this one. Question is why we make out of all such forms, why we assume this form. See, the boundary velocity was this one. Okay, so at okay. So, sin t is imaginary part of e to the power I t, because e to the power I t is cos t plus I sin t, right. So, and then you can adjust to the boundary condition by noting that u bar will be sin t if fy is equal to 1. So, imaginary means the sine part of it should match with the boundary condition. Had it been cosine, it would be real. So, then we will, because it is imaginary both sides, we will just take the inner part and do the algebra. I am not writing over and again imaginary just for simplicity in writing. So, this equation tells, so if you now take f is equal to e to the power mt as the trial solution, so you will get okay. Now, we have the condition that at t tends to infinity, sorry, this is y, right, not t, y. F derivative is with respect to y, right. So, if you take that at y tends to infinity, f is finite, then this term should not be there, that means C1 will be equal to 0. So, f is equal to C2 e to the power minus square root of I y, this is an exponential decay. Now, square root of I you can write in terms of I, because I is e to the power I pi by 2, this is cos pi by 2 plus I sin pi by 2, right. So, this is 1 plus I by root 2. So, square root of I, sorry, I have written the next step, this is square root of I. So, square root of I is e to the power I pi by 4, this is cos pi by 4 plus I sin pi by 4, this is 1 plus I by root 2. Okay. So, you can write f is equal to C2 e to the power minus 1 plus I by root 2 into this. How do you get C2? Straightforward. this boundary condition is valid at y equal to 0. So, at y is equal to 0 you must have f is equal to 1. So, f is equal to 1 at y is equal to 0, that means at y is equal to 0 this is 0, that means C2 is equal to 1. So, your solution to the problem is u is equal to imaginary e to the power I t into Fy is e to the power minus 1 plus I by root 2 into y. So, it is imaginary okay. So, you can see the solution is sinusoidal. So, the nature is same as the boundary condition, but there is a phase difference. So, the boundary condition was sin t, the solution is sin t minus a spatial coordinate dependence. So, I would suggest that you make a plot of this as a function of y and t using whatever plotting software you have, and that will give you a lot of interesting physical insight. So, in this lecture we have discussed about two very important unsteady problems in terms of exact solution of Navier Stokes equation, the Stokes first problem and the Stokes second problem. Thank you very much.